Hi everyone, welcome for the discussion. In this session, we are going to discuss about STP, Spanning Tree Protocol. Before starting the video, let's see on overview what are the things we have discussed in this session. In the introduction part, we have discussed about what is STP and what are the main advantages on it, what is layer 2 loop, broadcast term, and how STP prevents it. Then the components that involved in STP operations. Then how does this STP works? So three major steps and the rules and regulations for each steps. Then what are the STP states available? So let's start the video. And for more updates, please subscribe the channel and share with your friends. Let's start the video. So introduction. STP is a shortest form of spanning tree protocol. Earlier it was developed by Digital Equipment Corporation and later it was standardized by IEEE with a standard of 802.1d. So as per the L2 communication, the L2 communication, there should be only one active link. Okay, and if that active link goes down, there is a possibility for the communication failure. So in order to have a redundant link, if we have two active link between two L2 device, then it leads to a broadcast from a network layer 2 loop, which will affect the entire network. So in order to overcome this issue, this STP is introduced. Okay, so STP will allow us to have a redundant link. At the same time, it will have only one link as active and it will force the other link as the block state. Say for example, if there is a two device and we are having three link for between these two device, then immediately STP will see how many links are available between these devices, and if it finds any redundant link, that is one plus links, then it will have only one link as a forward state, an active state, and it will block other two links. Okay, and if the active link goes down, then immediately the other link which is in the block state will become the active. It will go through some election process and it will come to active state. So basically, STP prevents the layer 2 loop and stop the broadcast time in the network. At the same time, it allows us to have the redundant link. Okay, but still, though we have a redundant link in the network, only one link will be in active state and the redundant link will be in the block state. Once the active link goes down, only then the uh, redundant link will comes as an active. Okay, so by default, STP will be enabled in all the Cisco Catalyst devices. We no need to enable it. By default, it is enabled, and it is slow convergence because, as we said earlier, if active link goes down, it will go through some election process, and then the redundant link will come as an active state. So the time taken for it to come active is make it a slow convergence. So this is overcome by the another thing, that is a rapid spanning tree protocol that we will discuss on the next video. So in this video, we're going to discuss about a spanning tree protocol. So it's a slow convergence when comparing to RSTP. So advantages. So the three main advantages of using STP is it avoid broadcast term, the layer 2 loop, and avoid database inconsistency, and it avoids the duplicate frames. Okay. So first of all, let's see what is broadcast term. So I have taken a small scenario where I have interconnected three switches. So generally, it is not recommended if you are not using STP, but still, if you use STP, we can have it. So let's see what is broadcast term. If you're not using STP, then how this broadcast term is forward. Okay, so as per switching, we know that if any broadcast is received to a switch will forward the broadcast the packet to all other ports except to the port from the port where it is received, right? So for example, if switch B receives a broadcast packet from this port, then it will forward to other two ports, right? So now the switch A also will receive the broadcast packet from switch B, and switch C also will receive the broadcast from switch B. And so let's start from switch A first. Then once switch A received the broadcast from switch B, again it will broadcast, and so that except to this port, it will forward to this port. So already switch C received a broadcast packet from switch C, and now switch A also sends the broadcast packet. So in the meantime, for the broadcast which you sent for switch B, switch C also generates the broadcast. Once it received the broadcast from switch A, again switch C also will generate the broadcast. So this will go on endless, which causes the broadcast trumps. So this broadcast trumps, the layer 2 loops will make the network fluctuating, a network down. Sometimes if the broadcast term is too high, then the link will go up, it will go down and come up frequently. It starts to fluctuate, and even the device will starts to reboot, so it will bring a huge impact in the network. So this is what broadcast term is. And then database inconsistency is nothing but, say for example, if pc1 has an IP address of 10.0.0.1, and if it want to communicate with pc2 with IP 20.0.0.1, and for a layer 2 communication, apart from IP address, MAC address is required, right? So if it doesn't know, okay. Say for example, it's sending a ping request. Switch B doesn't know the MAC address of PC2, so it sends a broadcast R broadcast. So the R broadcast is sent to switch A and switch C. So once switch C receives the broadcast from switch A, again it will send the broadcast R broadcast asking for who is 20.0.0.1. So for that broadcast, PC2 will respond with its MAC. Then again, switch C will respond to switch B's broadcast with its MAC address. So now switch B have learned the MAC address to reach the PC2 via the switch C, right? At the same time, when it sends switch B sends the broadcast for the very first time, switch A also have received it. Okay, so now switch A also sends the same broadcast to switch C, and so, for that, as switch C is already having MAC address information of PC2, switch C will send its MAC address to switch A to make to understand it. If it want to communicate to 20.0.0.1, then it can communicate via switch C. So once switch A have those information, switch A will send its MAC address to switch B for the earlier broadcast request that is sent by switch A. So for the same destination 20.0.0.1, switch C will send its MAC address and switch A will send its MAC address. So the MAC address will not be consistent. It will be keep on changing. So this is what database inconsistency is. And at the same time, duplicate frame is nothing but, if PC1 want to communicate or send a frame to PC2, any packet to PC2, it will be duplicated. Once that is, it goes to switch A, switch C, and reaches the PC2, and the other one, other way is it goes to switch A, switch C, and it reaches the PC2. So for every frame there will be a duplicate frame sent to the destination. So in order to overcome that, we are using STP. So once we use the STP here in the network, it will see how many active links are there and how many redundant links are there. And if it finds, say for example, if STP detects there is a loop in the network, if there is an additional link, a redundant link is used in the network, then it will force the link to blocking state, and it will have only one active link. Maybe say for example, if once STP is enabled, STP may disable this port or this port, maybe this port, so that if a PC if PC1 want to PC1 want to be communicate with PC2, then it may go via PC1 to switch B, switch C, and PC2. Because either this port or this port should be down, right? So this is the main advantage of using STP. So three main advantages are nothing but, it avoids broadcast storm in the layer 2 network, avoids a layer 2 loop, then avoid database inconsistency, and avoid duplicate and multiple copies of data transmission. Okay. So how STP works? STP works with these three important stages in the three important steps. Step one is electing a root bridge. Step two is selection of a root ports, and step two, selecting designated and non-designated ports. Okay. So before starting before going into this, there are some terms and components that are involved in the STP. So I believe if we go through that and if we have a better understanding, then it would be easier for us to have a good clarity to understand how STP works in detail. Okay, so before going into this, how STP works, let's discuss about the components that are involved in the STP for better clarity and understanding. So basically, STP uses a tree-like structure and to form a loop-free topology. Okay. So the first thing is about a root bridge. This is the most important thing in STP. Root bridge is nothing but it's one among the device, one among the switch in the network. It's one among the device in the network is selected as a root bridge, and all other switches will be communicated. Uh, it will be connected to it. Basically, the communication between these switches, different switches, uh, will be done through this root bridge. Okay. Say for example, if there is five switches in the network, L2 network, one among the five will be elected as a root bridge. Okay, one among this five is the root bridge, and all other four will be connected to this switch directly or indirectly, and communication between the switches will be done through this root bridge. Okay, and STP has such an intelligence that it will automatically elect a root bridge. It has some election process, and at the same time, if a network administrator want to make a one switch particularly as a root bridge, he can do it manually. Okay, but still STP has this intelligence. So next one is a non-root bridge. So once a root bridge is selected, all other switches is a non-root bridge. In our example, we have seen with the five switches, right? So one among the five will be elected as a root bridge, and all other four, the remaining four switches is the non-root bridge switches. Okay. A root port. It's one of the important thing in the STP. A root port is nothing but a port in the non-root switch, and through which the non-root switch will be connected to the root bridge. So basically, a root port is a port in the non-root switch, and with that port only it is connected to the root bridge. Okay. So then, designated port. Each LAN segment will have one designated port. Say, for example, if a switch has a two LAN segment, then each LAN segment will be having one designated port, and every non-root switch will receive the packet will receive the data from a designated port, and it forward through its root port to the root bridge. So this is how the data is communicated. This is how the data is sent. So designated port, each LAN segment will be having on a designated port, and the non-root switch will receive the data, receive the packet from the designated port, and it will forward through its root port to the root bridge. Okay, and BPDU, it's a bridge protocol data unit. It's one of the main important thing in STP, because all the STP communication, all the communications between the devices are using this BPDU only, and devices using the STP in the network use this BPDU. Devices exchanges this BPDU and maintain the loop-free network, loop-free topology. Okay, there are two types of a BPDU. One is a configuration BPDU, the other one is a topology change notification BPDU, which is commonly known as TCN. Okay, TCN BPDU. Basically, BPDU will be consisting of information such like switch ID, bridge ID, switch priority, switch MAC address, and the port informations. So those informations will be available in the BPDU. So the next one is pathcast. So pathcast is nothing but every link type is associated to an cast. Say for example, if it is a fast Ethernet link, then the cast is 19. If it is a gigabit Ethernet link, the cast is 4. So as like that, every link it has its own cast based on the speed. Say for example, if it's a 10 gig link, the cast is 2. So as I said earlier, if it's a 1 Gbps, 1 gig link, gigabit Ethernet link, it's 4. And if it 1 STM, that is 155 Mbps, then it is 14. And for a fast Ethernet link, 100 Mbps, it is 19. As like that, we have a cast associated for all the link types. So it's very important in STP. We need to know the cast for all the link type. Okay. Based on this, some selection process will be going on. So it will be helpful if we know the pathcast. So now let's start to discuss on how STP works. Step one, root bridge election. Okay, as we said earlier, if there are five devices, five switches in the network, one among the five will be elected as a root bridge, right? So how it is elected? It is based on the 64-bit bridge ID. Okay, so a bridge ID is nothing but a combination of the switch priority and the MAC address. Every switch is having a priority value. By default, all the Cisco devices will be having the priority as like 32,768. Okay, so the bridge ID used in the STP is nothing but the switch priority plus the MAC address. Okay, switch priority. The default switch priority for all the Cisco devices is 32,768, and all the switches will be having a priority value. Okay, and this priority value can be manually incremental or decremented in the sequence of 4096. Either it can be decremented or it can be incremented in the sequence of 4096. If we want, we can do it, or else by default it is 32,768. Okay, say for example, as we said, right, if there are five switches and five of them are having a same bridge id, 32,768, the default bridge ID. Then switch which has the least MAC address among the five will be elected as the root bridge. So the tiebreaker here is the MAC address if the bridge ID is same. Sorry, if the priority is same. Okay. So step one, root bridge election is based on the bridge ID. So bridge ID is nothing but the switch priority and the MAC address. A device which has the least bridge ID will be elected as the root bridge. If the switch priority value is default in all the devices, is common in all the devices, then the tiebreaker is MAC address. If a device which has the least MAC address will be elected as the root bridge. So let's go for step two, the root port election. So as we said earlier, every non-root every non-root bridge should have one root port in it, and through this root port only it will be connected to the root bridge. And there is three important rule to elect the root port, and it is based on different setups. Let's see in a different setup how it is selected. Okay, here okay, so before going to root port selection, as we have a simple diagram here, let me show how let me explain how a root bridge is selected. Say for example, in my scenario, I'm having a three devices interconnected, switch A, switch B, switch C, and I'm having the priority value of I'm having all the the priority value of all the three switches is same. That's the default value, 32,768. So in an election of a root bridge, as per the rule one, the switch which has the least priority will be elected as a root bridge, right? But in my scenario, I'm using default value, so all the switches is having the same priority value. If in case, say for example, if switch B has a least something lower than 32,768 in the sequence of 4096, then it will become the root bridge. Switch B might have become the root bridge, but I'm using the default priority in all the switches. So the next tiebreaker is a switch which has the least MAC address will become the root bridge. So as my switch A has A, and here B, and it's C. So when comparing, A is the least one, so switch A become the root bridge. So this is how the root bridge was selected. And now we are going to about the see about the root port. Every actually once it is selected, it is the root bridge, and all other devices is the non-root bridge. This is one non-root bridge, and this is the non-root bridge. Every non-root bridge must have one root port to reach the root bridge. Okay, so it's a mandatory one. Every non-root bridge should have a one port called a root port to reach the root bridge. Okay, so now we are going to see about how a root port is selected. Okay, so as per the rule one, the port that has the lowest path cost to reach the root bridge is preferred. So basically, a port which has the lowest path will be preferred. Okay, so say for example, from root and I'm using a 1 gigabit Ethernet link to connect my root bridge and my non-root bridge switch B, and as well as in this side I have connected a fast Ethernet link, a 100 Mbps link, and this side I have connected a 100 Mbps fast Ethernet link. Okay, so for a 1 gig link the cost is 4. So if I want to communicate from here to here, the cost is 4, because for communication I have used here a 1 gig link. Okay, so the cost is 4. So at the same time, if I want to communicate from switch B to root bridge by this way, if it goes here and here, as I have used the fast Ethernet link, the cost here is 19 plus 19. So 19 plus 19, 38. Okay. So the past, the path, the cost path to reach switch B to root bridge in this way is 19 plus 19, 38. And in this way it is 4. So comparing to 38, 4 is least, right? So this port is selected as the root port. As like the same, coming to this switch, I want to select a root port from this switch. Okay, so I have connected a fast Ethernet link where the cast is 19, and at the same time, if I go through this way, then 19 plus 4 is 23. Comparingly, 19 is least one, so I have chosen this port as the root port. So this is the rule number one. A port that has the lowest pathcast to reach the root bridge will be elected as the root port. Okay, so let's discuss about the rule 2. So in rule 2, for better understanding, I have added a one new device. So it's not that as I added a new device, I need to check for rule 2. It's about the scenario. Okay. So in our in other scenario we have discussed, we have selected a root port, and for better understanding, for the rule 2, I have added this new device. Okay. Switch D is added, which it has two connections to both the devices. And as I have used gigabit Ethernet link in both the sides, the cast is 4. So in our previous rule, we have seen that a port which has the least cast is considered as the root port. But in this scenario, if you see, both of them is having the cast as 4, so I cannot apply that rule here. So I need to go for some other rule. Say for example, at the same time, if I have used a fast Ethernet link this side and a gigabit Ethernet link this side, then my cast be 4 here and my cast be 19 here. In that scenario, my rule 1 will be applicable, and I can choose this port as an root port. But in this scenario, I have used gigabit Ethernet on both the sides, so the cast is same. So the rule 1 will not be applicable. So I'm going for the rule 2. So rule 2 is nothing but if path are same, then the lowest bridge ID of the forwarding device is preferred. That is, bridge ID is nothing but the priority and the MAC address. Okay, so in this case, as the cast is same, it should see the forwarding device, means to say the upstream devices. So in this case, this is connected to the upstream device of this. These two are the upstream devices of this device, right? So we need to check which one is having the least switch ID, that is the priority and the MAC address. So in my scenario, I have the default priority for both the devices. So I'm the tiebreaker here is the MAC address. Comparing to C, B is the least one. So this is the device which has the least switch ID, right? So a port which is connecting to this device is selected as the root port. Okay, so I have elected this as the root port. Say for example, at the same time, if I used least priority here, then 32,768. Say for example, if it's a 4,096 something, so it should be least then comparing to 32,768, right? So in that case, it might become the least switch ID. Then this port might have been selected as the root port. But in this scenario, as per this scenario, this switch is having the least switch ID, bridge ID, and due to this, this port is selected as the root port. So this is the rule 2 for root port. Let's go for rule 3. So rule 3, it is applicable for this setup where my pathcast is same and my bridge ID is same. Okay. So if you see in this setup, I have two links to the same device. So in this scenario, I'm having a same cost. Say for example, though I have a two link to the same device, if I have one gigabit Ethernet and one fast Ethernet, comparingly, I can apply the rule number 1 and I can elect the root port. However, I'm having a gigabit Ethernet on both the side, or I'm having a fast Ethernet on both the sides. So the cost might be same, right? So rule 1 will not be applicable. And as per rule 2, I need to check for the bridge ID and the switch priority and the MAC address, as both the links are terminated on the same device. Obviously both are same, right? So rule 2 also cannot be applicable. So I'm going for rule 3, that is the lowest physical port of the forwarding device is preferred. So in this scenario, if you see, I have connected the forwarding device. It's about only a forwarding device, mean to say the upstream device. Okay, I have two links terminated. One is terminated on gigabit Ethernet 0/10, and other one is terminated on gigabit Ethernet 0/15. As 10 is least compared to 0/15, I have considered a port that is connected to this 0/10 interface is a root port. So this is the root port. This is the rule 3. So rule 3 is nothing but if pathcast and the switch ID is same, the lowest physical port of the forwarding device is preferred. So these are the three rules in selection of the root port, and these three rules will be applicable in this three types of setups. Okay, this differs from setup to setup, but these are the three setups where you can apply. And so next step. So in the previous earlier we seen about root bridge election and root port election. Now we are looking for selecting a designated and non-designated port. Generally, a designated port is a port which is in the forwarding state. However, it will not directly directly in the forward state. It will go through a step-by-step process from blocking state to listening state, then to learning state, and only then it will be moving to the forwarding state. Okay, and the non-designated ports will be in the blocking state only. So we'll leave it. So there are some criteria. There are some rules to check for the designated ports. To elect the designated ports, it looks similar to the rules of the root port selection. However, there is a small changes, but it's very important. So if we compare these three rules, it is same as like the three rules which is available for the root port election. See, uh, the least path cost should be considered, and the least switch ID should be considered, and the least port number should be considered. However, the main difference here is for a designated port, we are not supposed to look for the upstream device. Rather, we need to consider the local device. Say for example, if you look for root port selection rules, we should we should be looking for the upstream device, that's a forwarding device. But in the designated port, we'll be looking for the local device only. Okay, so the same rule is applicable for the designated port as well, but here we'll be looking for the local device instead of forwarding device. So say for example, in the existing scenario, once we have found the root port, now we need to find the designated port. So we may not know which is the designated port in this link. So how we found is, so cast is 4 in general. It's the same link. So cast is 4. So rule 1 is not applicable. Then as per rule 2, a device which has least switch ID is preferred. Least local switch ID is preferred. So obviously switch B is least, then switch C as its MAC address is BBB. So this port, a port in switch B, is considered as the designated port. Okay, but in a root port, we have seen the forwarding stream, but forwarding device. But for a designated port, we should concentrate on the local device. Okay, so rule 3 is for both device has the same switch ID, the device has the least port number is connected. It's just like this setup. So I'm just referring this as a setup, but it's for the root port. So if you see setup like this, then rule 3 is applicable. You should look for the least port on the local interface. However, for a root port, you'll be looking for the upstream interface, but for the designated port, we should concentrate on the local device least port. Okay, so these are the main three steps. So this is how STP works in three steps. Step one is selection of root bridge, and step two, selection of root port. Step two, designated and non-designated port selections. So once this designated port is selected, then obviously this is a non-designated port and this port is blocked. Okay. So these are the states that's involved in the STP operations. First one is blocking state, listening state, learning state, forward state, and disable state. In blocking state, it will not forward any frames, it will not learn any MAC address, but it will receive and process only the BPDUs. A port before going to the listening state, it will be in a blocking state for 20 seconds. In a listening state, it listens to the STP message in the form of a BPDUs, and it will learn the network topology, how it is configured. Okay, and in listening state also, the port will not forward any frames, and before going to the learning state, it will be waiting in the listening state for 15 seconds. And once it comes to the learning state, it will begins to process the user frames and also starts to update the MAC address table. However, it will never forward the frames. Okay, and before going to the state, it will wait in the learning state for 15 seconds. Once it goes to the forward state, then it just do the normal operations as like forwarding and receiving all the frames. So these are the main states of the STP. And one of the main disadvantage of STP is about the convergence time. as we said earlier, it is slow convergence, because if active link goes down, and the other link which is in a block state needs to come active, right? So if you see, it needs to wait for 15 seconds in the listening state, and again 15 seconds in the learning state to come to the forward state. So at least it needs to be it wait for 30 seconds, right? So the convergence time is too slow. So in order to overcome this, the rapid spanning tree protocol is developed. So let's discuss about RSTP in our next video in detail.